are useful to watch again? Okay, that's good. That's good. The quality is okay? Can you see? Can you see the board? All right. Let's start, and let's start where we stopped. This is our functional analysis class. 2019. This is lecture, if I'm not mistaken, lecture number 7, right? Let's talk a little bit about the so-called uniform boundedness principle. Also known as the Banach Steinhaus theorem. This is the topic for today's class. Let's review a little bit of what we had. So some announcements before we start, and then we review. So first, announcements that I would like to make to you. So next homework 2, let's make it for Friday, this Friday. Which day is this Friday? Today is 19/22, if I'm not mistaken. Very good, 22. Homework 1, I'm still taking a look at yours. I'll probably get back to you by this Friday next week. So, I'm trying to preliminary schedule our exam 1 for March 15, okay? So this is preliminary. You guys haven't done that. So 15:30 to 17:30. This is a preliminary schedule. On this week of March 11th, so March 11 to 15, we will have no class. I have to make a trip to Pakistan, so this week you're going to be off the hook for functional analysis, just at the end of the week, so you have the time to review everything. And March 15, I will leave a little exam for you guys to have fun here, and one of the postdocs will help me getting it done. Okay, so these 2 classes on the week of March 11 and 15 will be given probably later on. Okay, so these are the news. Where did we start? So last 2 classes we were taking a look at the Hahn-Banach theorems. Right? And you guys by now should have the chance to explain to me how do you interpret the geometric version of the Hahn-Banach theorems, right? So if I give you 2 convex sets, you can separate this. So let's review what we looked at in the last class. So one of the theorems that we proved last class was if I give you 2, say E being a normed vector space, A and B containing E be 2, let's say 2 non-empty convex sets, one of them open, let's say A open, then there exists a closed hyperplane which we denoted like this. Let's see. It's a linear functional f, the set of the points where f of x equals to a certain real number alpha that separates these 2 convex sets, A and B. That is, i.e., meaning f of a or f of x less than or equal to alpha less than or equal to f of y, any x in A and y in B. So if I give you 2 convex sets, A and B, one of them open, you can find a hyperplane that separates them. Not strictly separates, so this is the theorem 2 that we saw at the end of the class. Same situation as before. In the norm vector space, A and B, two non-empty convex sets. Now let's assume that A is closed and B is compact. So if I assume that one of my sets is closed and the other one is compact, you can actually find a hyperplane that strictly separates. So this is a closed hyperplane, say F equals alpha, that strictly separates the sets A and B, comma. That is, there exists an epsilon bigger than 0 such that f of x is less than or equal to alpha minus epsilon, which is less than alpha, which is less than alpha plus epsilon, which is less than or equal to f of y for any x in A and y in B. Okay, so it can actually strictly separate this thing. This is going to be useful. You have seen a couple of exercises whenever you have to extend. So the analytic version that we had before, where you can extend linear functionals, was used to prove these things. And one of the nice applications of these geometric versions of the Hahn-Banach, for example, comes from the following fact. So let me, how do I write this? So proposition, let me write a proposition A, is actually a corollary of this. So let us, instead of calling proposition, let's call corollary, which is so let A, say be a closed subspace. If A is a closed subspace of E, okay, and A is not E, it's not the whole space, we let x0 not belong to A, and there exists a functional f such that, say, f of x is equal to 0 for any x in A, and say f of x0 is bigger than 0. So if I give you a closed subspace, which is not the whole space, you can take any point outside of it and construct a functional that vanishes.
Must it be closed? Is it not enough with the closure?
Well, you can take a closed subspace, or you can take a subspace. If you want, you can write, okay, let A be a subspace such that A bar, the closure, is not the whole space. Okay? Let x0 not belong to A bar. Then there exists a functional dual such that this is true.
The other one is substitute?
Yeah. I mean, if you take a closed subspace, yes, yes. If you want, you can do this. So, yeah. So, and the proof of this is very simple, right? If you have A, the closure of A is closed and obviously convex, this is a subspace. The point x0 is obviously a compact. So you can use this version of the Hahn-Banach theorem to separate a closed and convex set of a compact and obviously convex set because it just has one point. So this means that there exists, say, an f in the dual such that f of x0 is strictly bigger than f of x for any x belonging to this closed set, A bar. This is what this theorem says.
How do we know A bar is convex when it's not?
A bar is a subspace. A is a subspace, so A bar is a subspace as well.
So by that, A bar is convex. Sorry.
Okay, so you agree that A is convex, right? A is a subspace. So I want to show this A bar is also a subspace.
Okay, the closure of the convex set is also closed.
Yes.
The convex set is also convex.
Yes.
All right.
This is what I want to have. Right? Yeah. I mean, that's exactly what you said. The closure of a convex set is also convex. This grain. There exists a functional such that f of x loses to f of x0 for any x in this set, but this is a subspace. Right? So you could take this equation and change x by minus x. Okay? And you could also multiply by lambda. So these things must hold too, right? If you change x by minus x, this holds too, because minus x is also in the subspace. And if you multiply by lambda, you use the linearity, all of these things should hold, because all of these elements are in the space. So the only thing for all of this to happen, the only condition, the only possibility that you have is that if this guy is actually identically zero in the subspace. Because if this guy were positive, you could multiply by lambda and break this condition. If it were negative, then you would take f of minus x as positive and you could multiply by lambda and break this condition. So the only possible way, from this you conclude that f of x must be actually identically zero for x in this square subspace. Okay? And this is how you're going to prove. So I just want to make, so this concludes the proof of the statement, right? So whenever you have a subspace that is not the full space, that the closure is not the full space, you can take a point outside and construct a functional that is not zero on this particular guy and it's zero in the whole subspace. Okay, this is how you're going to prove that some certain subspace is dense in your whole set. Okay, so use this fact when you want to show that a certain subspace A is dense in E. Right? You want to show that A bar is actually equal to E. So whenever you want to show that a certain subspace is dense in E, okay, I want to show that the step functions are dense in LP. LP not infinity. The continuous functions are dense in LP or something. Whenever you want to show that a certain subspace is dense in a certain space, all you have to show is that for any given functional f, if it vanishes everywhere in A, then it's identically zero. Okay? So if you prove this fact, okay, give me any functional, if it vanishes everywhere in A, then it has to be identically zero. Okay? Then this thing that I just proved here cannot happen. The conclusion is that A is going to be dense in E. Because if it were not, then there would be a functional that vanishes everywhere in A, by continuity it would vanish everywhere in A bar, but it's not identically zero.
Sorry, where do we get that A is convex?
A is a subspace. Every subspace is a convex thing.
Yes.
Okay. I start with the subspace. Sometimes you even start with a subspace generated by a certain number of vectors. So if this is the subspace generated by a certain family, all you have to show, so if you have a certain family of vectors, and you take the subspace generated by them all, by all of these guys, say the Fourier bases or something, right? And you want to show that this is the subspace generated by these guys is dense in the whole space. All you have to show is that give me any linear function of f that vanishes in these basis elements, then it has to be the identically zero function. Okay? So we're going to be using this fact later on in the course. Okay, this is enough for a review of what we did last week. Now, let's move on to today's topic. Let's see. So we're going to start reviewing this so-called bare category theorem, and which is the following. Let me give my notation. Let X be a complete metric space. I assume everyone here is familiar with the notation. Complete metric space, right? We haven't actually discussed, we were always discussing here vector spaces, norm vector spaces. Of course, a norm induces a metric, but you can talk about metric space. It's just the space where you have a distance between 2 points, right? This distance of x and y has to be something which is bigger or equal than 0. It's obviously just 0 and x is equal to y, and it verifies the triangle inequality. Okay, this is what the metric space is. It's a space with the distance between 2 points t. It doesn't need to be a vector space. It doesn't need to be a norm. Whenever you have a norm, you can obviously define a distance between 2 points by just putting the norm of the difference. Okay? So every norm vector space is obviously a metric space, but the converse is not true. And complete is what we all know. If I give you a Cauchy sequence, the metric space, then it will have to converge to a point in the space. So let X be a complete metric space, and say Xn, and from 1 to infinity, a collection of closed sets with empty interior. So with interior of Xn equals an empty set. So a collection of closed sets with empty interior. And the conclusion of the theorem is that the interior of the union of these sets is still empty. Okay? So if you try to feel, if you get me on this plane, a countable collection, it has to be a countable collection of closed sets with empty interior. Right? Did we all learn in topology what the interior of a set is? It's the set of the points there for which you can put a little ball inside. Okay? So no points in my set Xn, you can put a little ball inside. Every point when you put a little ball, there will be point inside and point outside. Every point is a bounded point. Okay, so if you try to fill your whole set with closed sets with the empty interior, you cannot do this. I mean, the interior of the union will keep being empty. When you think about it, try to fill the plane with lines. Get me a line is a closed set in the plane with the empty interior. If I try to fill the plane with a countable union of lines, of course, I will keep having empty interior. There's no way I can fill the whole thing. Of course, if I could use an uncountable, then we could fill it, but not like this. Did you guys prove this theorem in topology? Or no? Okay. This is very useful. It's very interesting. So let's prove it now. You will be using this. This is one of the most fundamental theorems in analysis. You'll be using it in many different occasions. Let's see. Bear is the name of the person who proved it, and this is usually called Bear category theorem. You say, why category? I don't see any relation to this word category here. Is that Bear, when he was studying these sort of sets and this sort of unions of closed sets or unions of intersections of some things, he was in his studies. He was defining different categories of sets. So he called some sort of sets. So these are my sets of category 1, these are the sets of category 2. And so he was kind of not giving names to the different categories of sets that he was studying, but giving like numbers. This is category 1, category 2, category 3, and so on. So this is usually referred to category 1 Bear sets. Okay? So whenever you hear this word, this theorem, Bear category theorem, this guy. This is an equivalent formulation. So I gave you a formulation with closed sets with empty interior, right? So it's totally equivalent if you take the complement of these sets. So Xn complement, what are these sets? So this is a collection of open sets and dense. Okay. So if Xn is closed, then the complement will be an open set. If Xn has empty interior, this means that the complement will be dense. Okay, so if I give you a collection of open and dense sets, then the conclusion is that, so open and dense set is a very fat set. It's a set that populates the whole space, right? So the conclusion of this theorem is that even if you take the intersection of these Xn's complement from 1 to infinity, intersection of accountably many open sets doesn't need to be open anymore, all right? But it's still dense. This is still dense. So if you take the intersection of all of these guys, this is essentially the union of Xn from 1 to infinity complement. Okay, the complement of the union is the intersection of the complements. So if this guy is going to have empty interior, that is because this guy is going to be dense. Okay, so if you can see from this point of view, if you prefer. Now I'm giving you a lot of open sets which are very fat that populate my whole space, and you're going to take the intersection of these guys, all of them, it's going to be still be big in some sense, still going to be dense. Okay. All right. Do we all see that these are completely equivalent statements? I'm just using here the property that if Xn is closed, then the complement is open. If Xn has empty interior, the complement is dense, and that the complement of the union is the intersection of the complements. So if this guy is going to have empty interior, that's because this guy is going to be a dense set. So let's try to prove in this second version. So proof. Let's go and work with the open sets today. Okay? So let G be this set here. Big G be this set. Intersection of xn complement, and from 1 to infinity. I cannot stress that this is a countable collection of sets, okay? I can't stress this anymore. Let G be this set. I want to prove that it's dense. So this means that for every point that I pick, for every point x0 that I pick, and I make a little ball around x0, I have to have a point of the set G in this little ball. So let's pick a point. So let us pick x0 in your whole set X, and a little ball B, which is the ball center x0 and radius r. Okay. So you got my point x0, and I got the little ball here. I have to prove that around this ball there has to be a point in G. And I call this ball B. Maybe I can call it B0. It's a ball center x0 and any radius r. So this is given. Okay, so we have to prove, we must prove that there exists certain, say, x that belongs to G intersection B0. Right? This is what we have to prove. Okay.
So, sorry. What we mean by dense, that any neighborhood around the point intersects the set. That's what we mean by dense?
Yeah, a dense set, so let's say A is dense in X. If I give you any point in X, any x0, and any little ball in X, it has to intersect A. Okay, so any neighborhood in X, any little open ball in X has to intersect your set A. So
Are
this.
they different from x naught?
Huh?
Are they quite different from x naught? Because if x naught is in A, and it's intersect with the point x naught.
Different than x0.
Your x0,
Different.
It's not.
Not in G.
No, it doesn't matter. Actually, there's a definition of density. Every open set. If we take every open set, in this case, we can find it.
You know, if you pick,
this x0 doesn't have to be in G, of course.
that's what I'm saying, that if x naught should be in G,
If x0 is in G, then you're okay. You can take x0 as this point in the intersection. Okay? But of course, the interesting case is when x0 doesn't belong to G. But the point is that any open set in X must intersect the set A. This is to be dense, right? It's equivalent to saying that the closure of A in X is the whole X. Okay. Okay, so how do you do? Now I have to use what I have. I have to use what I have in my hand. So the only thing that I have to use is that these xn complements here, they are open and they are dense. Okay. So if they are dense, so I can say that since the x1 complement is dense in X, there exists an x1, there exists a point x1 that belongs to this set intersection this ball, this big ball, right? I took an open ball. Since my set x1 complement is dense, there exists a point x1 here inside this ball. Moreover, since x1 is actually open, since x1 is, since the set x1 is actually open, I can actually find a little ball around x1, so I can actually place a little ball around x1 with radius r1, totally inside the set. Okay? I can make a little ball here. I can even make it a closed ball if I want, by just taking half and taking the closure. There's a little ball that is contained in this set. Both are open, so if a point is contained in this set, so there's a little closed ball that is contained in this set. Good. Alright, so this is essentially an algorithm that you're going to run. Okay? So just for the sake of the argument, let us choose R1, say less than R0 over 2. Let's do it again, R0 over 2. Let's call this R0. We chose your point x1 and your radius R1. Right? And then you do it again. Since x2 complement is open and dense, since it is dense, you can actually find a point x2 inside this little ball here. Right? It's an open ball. You can find a point x2 here. And since it's open, you can actually not only find a point x2, but find a little ball that is inside. So there exists a little ball B of x center x2 and radius R2, such that the closure is contained in this x2 complement intersect. Let's call this ball B1. B1. Let's call this ball B2. Okay. And you can choose how small this radius is, and you choose this R2 to be less than R1 over 2. You always choose the radius to be, say, at most half of what it was before. And you keep doing this process. Okay? So you keep running this process to generate these balls, say Bn plus 1 of a center Xn plus 1 and a radius Rn plus 1 is contained. So this ball here is called Bn plus 1, contained in the Xn or Xn plus 1 complement intersection Bn with Rn plus 1 less than or equal to Rn over 2. Okay, so by this property of this each Xn complement being open and dense, you go and choose these points and these little balls one inside the other. Alright, so we are essentially done. Let's just interpret this. So you have constructed a sequence Xn, little xn from 1 to 3. This is a Cauchy sequence. Do you all agree? It is a Cauchy sequence because every guy that I put is inside the little ball with the center in the previous guy and a radius that is getting smaller and smaller by powers of 2. Okay? So this is a Cauchy sequence. Therefore, this Xn converges to a certain point X. And I claim to you that this is the X that I'm looking for. Okay? So X obviously belongs to my space. X I wanted to show that it belongs to G and to B0, right? In fact, since I started with B0 here, and I say that again?
It's a nested sequence of closed sets.
Nested sequence of closed sets. Yes, this is a nested sequence of closed sets if you take the closed balls, right? The intersection is not empty. That's what I'm saying. It converges to a point X. Okay, so this is in the intersection of everyone, right? So this point x, you will see that it belongs, since x n plus k belongs to the ball Bn closure for all k bigger or equal than 0. So by construction, this xn belongs to the ball that we call Bn bar, closed ball. So xn plus k, if I keep going in the sequence, I stay inside this ball forever. Right? So if I freeze n and send k to infinity, so this means that my limiting point x belongs to this ball Bn closed for all n bigger or equal than 0. Okay? But Bn bar was actually contained where? Bn bar was contained in Bn minus 1. For n bigger than 1. So it's for n bigger than 1. Okay? So this means that my x belongs to all of the open sets. Oh, so this Bn bars was actually contained in xn, so I actually don't need this. So I don't need this. For all n bigger than 0. So this is already enough to conclude that my x belongs to G. Why? Because this Bn bar is always contained in xn complement. Okay, so it actually belongs to all of these guys. So my x belongs to all of these guys. And it belongs to the original ball B0. Why? Because it belongs to the B1 bar, and B1 bar was contained in B0. Alright, so this is the proof. Okay? It's not as, once you see it's not that hard, but you have to put the pieces together in this nice way. Okay? So we have proved this result. Now it's in our pocket to use. There's category theorem. The union of open sets that are dense, the union of closed sets which have empty interior is still some set which has empty interior. I'm not saying it's closed anymore. You can have a countable union of closed sets. It may not be closed anymore, okay? But it still has empty interior. If you want to go to the open set equivalent formulation, if you have a countable collection of open and dense sets, the intersection, which may not still be open, but it's still dense. Good. This is powerful stuff. So you will see very frequently in mathematics, especially in analysis, that usually there's not so much of hard stuff. Something hard is just a collection of small pieces of simpler things. Okay? So this in itself is simple, but it has powerful applications. So something hard is just a collection of easier things put together. So have this in your mind. So once you start collecting these things in your pocket and start learning how to do this, it's just a matter of combining all the pieces together. Something hard is just a bunch of easy things put together in the correct order. This is frequently true for mathematics. This is a little bit of what you have to discover later in your life. But different topics in mathematics, they have different flavors. One of the reasons that I like analysis is that the objects that you deal with, that you are dealing with, are generally basic stuff that you can define, and in one class I can present to you and discuss what the object is, what the theorem is, and you can understand the proof, you can understand what I'm talking about. So it's a bunch of easy things that you put together, but the difficulty of the fields of analysis, and some PDEs, some harmonic analysis, some real analysis, and so on, the difficult doesn't lie in the definition of the objects. Usually you can define all the objects simply and so on. The difficulty is how you put these pieces together to prove the theorems, which sometimes are easy actually to state, but the difficulty lies in the proof. Some other fields, need a much more refined, background, and you have to understand the definitions and so on. So fields more like algebraic geometry, you have to have the objects are more difficult to define, and you have to have a certain background and study hard for a couple of years to be able to actually understand the statement of the problems and appreciate the beauty of the subject. I mean, and then this is a little bit of this game that you have to play, which field you are more inclined to, and so on. I appreciate all of these things, but I recognize that sometimes I prefer to deal with simpler objects than with the much involved in technical things. Let's see. Are we all okay? So you understood this. I'm saying this is powerful stuff if used correctly, and I will show you exactly what I mean. So let me erase here. Alright, so I think we are ready to prove the main theorem of today. Banach house, or also called uniform boundedness principle. As a matter of fact, before I state the theorem, I have to define to you something. Let me erase this part of the board if it's okay. Like, is that okay if I erase here now? Somewhere. Carlos is still copying. Oh, that's okay. If you're copying, I'll wait a little bit and we can talk a little bit more nonsense in this class. The best part of the class is to talk nonsense. Okay. So if we have two E and F being two normed vector spaces, okay, so let me give you two normed vector spaces. I can consider the space of all the linear and continuous maps between E and F. So let me call this L of E to F as being the space of all F's from E to F which are linear and continuous. Linear and continuous functions from E to F. As we have seen before, continuous in this set at any point, since it is linear, is equivalent to being continuous at 0, and to be continuous at 0 is equivalent to be bounded. So I can also say linear and bounded maps from E to F.
What do you call the space of linear maps from E to F?
Not necessarily continuous, you mean? I don't know, the space of linear maps from E to F doesn't have to have a letter. If you don't want to call this L, just call whatever name comes to you. Let's call here L of E to F, the linear and continuous and bounded maps from E to F. Okay? This is itself a normed vector space. That this is a vector space is clear, right? You have two functions, f and g. From E to F, you can add two functions and construct the function f plus g, and you can multiply the function, so f by lambda f. Okay, let's say these are two normal vector spaces over the same field R. That's it. Okay. But the nice thing is that this has a norm associated to it. And the norm of this, let me actually call, instead of, to differentiate between the functionals that we have seen before, let me call T. Because F we were usually denoting for functionals from E to R. Here I want to go to another vector space which is not necessarily R. So if F is R, this is the space which I was calling the dual space, E star, okay? But if F is any generic other norm vector space, I'm calling L from E to F. And I'm calling an operator here T. So the norm of T in this space, sometimes called the operator norm, is just defined as being the supremum as we had before. The norm of T of X in F for any X belonging to E with norm of X in E less than or equal than 1. Okay, it's exactly the same definition as before. It's the supremum when you take the unit ball in E, the maximum that you get on the other side for the norm. Of course, if F is the real number, this is just the usual absolute value of T of X. Okay? This is not necessarily a Banach space anymore. This is a norm, but this is not a complete space unless when your F here is actually a complete space, then this guy is going to be complete as well. But this is the definition of the operator norm. So in other words, you always have that T of X on any vector, T of X in F, is less than or equal than the norm of T in this space times the norm of X in E. Okay? Recall that a bounded operator is an operator that satisfies this for some C. This is a bounded operator. The smallest possible value of C that you can put here is actually the norm of T. Okay? This is what's the definition of bounded. And the smallest possible value of C that you can put so that this inequality is still true, the smallest possible value of C that you can put is this number here. Okay? Is that clear to you guys? I mean, this is a little bit subtle, but it's important. Whenever you have a bounded operator, this means that you can put a constant here, say 100, such that this is true. T of X in this norm of T of X in this space, in the target space, is less than 100 times the norm of X in the original space. But you can ask yourself, okay, so this is a bounded operator. There is a constant such that this inequality is true. This means that the operator is bounded. Now you can ask yourself, is 100 the best constant that I can put there? Would the inequality still hold with 99, 98, with 10, with 1? Of course, if it holds with 100, it holds with 200, right? So I can put any guy bigger, but can I put something smaller? So this is actually finding the smallest value of the constant, is actually finding the operator norm, you know. So this guy defined like this, so the guy is the supremum of the value that T of X attains when X is in the unit ball here. So this means that if you scale things, so if the norm of X is not 1, but it's 2, I mean, I would just scale this constant by 2. So this means that this inequality here holds with this constant C. But it doesn't hold with anything less than C because this is defined as the sup of these things. Right, so, yeah, in other words, if you just move this norm of X down, so what you're saying is that this C has to be bigger or equal than T of X in F over X in E, for all X in E. This constant C has to be bigger or equal than this thing. So by dilation, you could dilate up and down. You can assume that this guy in the bottom is 1. So what you want is that C is bigger or equal than T of X for all X of norm 1. So C has to be bigger or equal than the sup, which is actually this. Okay? This is how we prove that C is bigger or equal than the sup, and of course the sup also works. C is less than or equal than the sup, and then this is okay. So a lot of problems in analysis is a lot of interesting problems arise in actually computing the operator norm of certain maps. Okay?
After the problem of deciding if they are bounded in the first place.
Absolutely, yes. So there's a lot of nice problems in analysis and PDE to decide if the operator is bounded or not. Once you have decided if it's bounded, what is the operator norm? Once you have actually found the operator norm, are there extremal vectors? Are there vectors that actually realize the equality here? So who are the extremal vectors and who are these extremal functions? Can you characterize them and so on and so forth? So these are a sort of, in every functional inequality that you have, these are very, very interesting things. Right? So I'll give you an example, but just maybe we may come back to this thing. We proved in the first class here Young's inequality, if you remember, right? So we proved that this, but on certain norm R was less than this with a certain norm P, with this with a certain norm Q, if I'm not mistaken, this was the case, right?
One is not based, there are some smaller estimates for less than 1.
Yeah, so we're proving this with constant 1, right?
Yeah.
But this estimate generally holds with a constant which is smaller than 1. And this is very hard to prove.
Sorry, what's that?
This is Young's inequality, right?
Yeah, but what's the norm here? From what space to what space?
Well, this is a map that sends what? T from LP cross LQ to LR, right? I'm going to take a pair of functions, f and g, and I'm going to map to f involve the t. So this is not a linear, well, yeah, this is actually a bilinear operator. It's linear in each entry. But you can talk about the norm in the same setting here. If you look at this is your E, this is your F, if you want.
So what's the
This one is same with if we take a fixed F, in this case from LQ to LR.
You can also do that, yes. You can fix a G and you can map, you can fix G and you can map from LP to LR, yeah. But you can,
What's the constant? How far away from 1?
the best functions that you can put here are Gaussians. So if you just take f equals g equals a Gaussian, and you compute what this is, or what this is, or what this is the value of the constant, if you just divide. This is a very, very, very deep result, proved in 1975. Okay? That the best functions that you can put in this inequality are the Gaussian functions. Anyway, okay, so now if I have two vector spaces, I can consider the bounded and linear functionals from one space to another one. This is also a normed vector space, and this is the norm, right? This is the definition of the norm. The Banach-Steinhaus theorem states the following. Let me write down to you, because it's a very, very surprising statement. Let E and F be Banach spaces. So I'm taking here the complete vector spaces, non-vector spaces, and Ti, a certain collection and I will emphasize that it's not necessarily countable, of linear bounded, which is the same thing as saying continuous, right? Operators. Is from each of from E to F. add the supremum over this collection of all the norms Ti of x in F, but this is finite, for each x in E. So this is the assumption. For each x in your space E, for each fixed point x, you assume that the pointwise bound holds. So if I take Ti and apply this vector x, and I take the norm in the other side, that this is a bounded quantity. Then, the conclusion is that the operator norm of these guys is bounded. There is a uniform, so the supremum of the operator norms is bound. There is a uniform bound for all of the operators, right? That is, there exists a certain constant c bigger than 0, such that Ti of x in F loses to this constant c times for all I in a family and all x in P. Think a little bit about this statement. So the thing is, you have a vector space here, E, a Banach space, and you have another Banach space here, F. You have here a bunch of operators indexed by some family, certain index set I, not necessarily a countable family or whatever. So we have a bunch of operators here, linear operators from E to F, linear and continuous operators. Each guy is linear and continuous, each guy is linear bounded. And the claim is that if this pointwise estimate holds, so if you have a pointwise estimate for each fixed guy here, x, if you just apply the Ti of x for all I in the family, and you don't go to infinity in the norm, if this holds for a pointwise, then this pointwise estimate implies a global estimate. It implies that the norm of these operators, I already knew a priori that they were all bounded, but they have a uniform bound for the operator norm. Okay, so I cannot have, say, T1, T2, norm 1, norm 2, norm 3, norm going up. To have that, I would have to violate this. This is a very, very, very powerful tool, and it's very strange when you look in principle that such a weak thing, so this is just a pointwise estimate, would have to imply a global estimate like this. That all of these operators are uniformly bound. The proof is an application of the Baire category theorem, as I told you. So you see a little bit of the power of Baire's category theorem going on here. So let's see.
Sorry, do we first take the supremum over all this inequality?
Assume that, so let me write it, for each x in E, this is fine.
So, for each x, the supremum depends on x.
Yes. The supremum might depend on x, but it's fine. Then, supremum of the operator norms of the guy is fine. The key idea for the proof we want to use, I'm telling you that we want to use Bayes' category theorem. So we have to define those sets appearing in Bayes' category theorem. Okay? So once we have defined them correctly, the rest of the proof will just follow smoothly, as we'll see. So let us define the sets. Let me call Xn I want Xn to be the set of all X in my space E such that Ti of X is less than or equal than N for all I in my set of indices big I. For all the operators, so this is my set Xn. So this Ti of X is always less than or equal than N. Is that clear? So from the definition, is it obvious to you guys that this set is closed? If I fix an N, the set is closed. Do you guys all agree? The set is closed because all of these operators are continuous, right? So if I take a sequence of points 0 xn belonging to this guy, 0 xn converging to x, so all Ti of xn is less than n, Ti of x will also be less than or equal than n by continuity. Okay, so this is why I'm putting less than or equal to. So this is a closed set. Right? Since all Ti's are continuous. Are we good?
Yeah, the H1 is continuous and the normals is continuous, the composition of both is continuous.
What else do you know? So what does this hypothesis here tell me? Empty interior? No, but what does this hypothesis here tell me? What can you say about the union of all these xn's? It's equal to x. Why? It's equal to E. Why?
Because for any point, we know that at some point it will be less than or equal to.
Yes. So this hypothesis here tells me that for any point in E, this soup is finite. So therefore it will be less than something, less than a billion, and it will start being inside the x 1 billion. So for every point x, there is an n such that x belongs to xn. And of course, these sets are all nested, right? So the union of all the xn's is my whole space E. Good. Now, you have a bunch of closed sets whose union is the whole space. From Bayes' category theorem, what can you conclude from that?
At least one.
That's
Yeah, so this is generally how you use Bayes' category theorem. It's like a counter-positive thing here. Like all the sets are closed and the union is the whole space. Therefore, they cannot all have empty interior. Because if they all had empty interior, the union would have to have empty interior, but it would not be the whole space. Okay. So, by Bayes' category theorem, one of them, there exists, say, n0, such that the interior of x and 0 is not the empty set. Okay? Therefore, now the proof has to continue. The show must go on. So if you find this, what's the next step?
There's an open set inside
The next phrase has to be this one, right? So take a certain point x0 and a certain ball with radius x0 and radius r that is inside this set. Okay, so you have your set here x and 0, there's a point x0 and a little ball that you're inside. Maybe you can even put a closed ball. If you want. Let's see. Right? Aha, but what does this mean? This means that, well, if this whole ball is inside this set, this means that Ti of x0 plus rz, this is the ball, right? F is less than or equal than n0 for all z belonging to the ball of a center 0 in this one, if you want. Right? X0 and R with
Now use the triangle inequality to deduce the...
Yes, so now I'm going to use the triangle inequality in this form. So now use the triangle inequality. I actually want to use that this is for all z's in the unit ball and all i's in the collection of indices, right? All i's in the collection of indices. I'll use the triangle inequality in this form. That this is bigger or equal than Ti of Rz minus Ti of X0. Okay, so I'm going to use the triangle inequality with the minus here. Let's say this guy is less than this plus this. Okay? And this is less than or equal than X0. So all that's left is to actually move this Ti of X0 to the right. And I'm using the linearity here to say that R times Ti of Z in F is going to lose to this N0 plus Ti of X0 in F. And I'm done, right? Because then this implies that Ti of Z in F would be less than 1 over R times N0 plus supreme I of this guy, which is just a fixed number. So this is bounded, this is pointwise bounded by a certain number, plus N0 divided by R, all of this is fixed. Ti of Z for any Z in the unit ball is bounded by this whatever number. So this means that the norm of Ti in this operator norm is bounded by this number that we call here C. And this is the proof. Okay? Very interesting application of Bayes' category theorem, showing all the power of this theorem now. All the power of Bayes' category theorem to prove the Banach-Steinhaus. So, from now on, one more weapon to put in your pocket. If you have family of bounded operators, that is pointwise bounded, this implies a uniform bound. And I assume that the hypothesis of the theorem that E and F were Banach spaces. Where did I use it? Do I actually need it? In bare category theorem, I wanted E to be complete, right? So all you actually need is E to be complete. Did I use in the proof that F needs to be complete? Didn't use that F needs to be complete. So if you want to go...
Not here, but in bare.
For the bare category theorem, I need the fact that E is complete. So E is actually, E has to be a Banach space. But F can only be a non-vector space if you want. I didn't use in the proof that F was a Banach space. So if you want to weaken this a little bit, you can assume that E is a Banach space and F is just a non-vector space if you want. But for simplicity, we stayed with E and F, Banach space, okay? Most of the situations you'll be dealing with are like this. Are we good? Isn't this phenomenal? Now let's start using these things. All right. Let's see. Let's do some corollaries with this. Now we can draw some interesting corollaries with this, and I really hope that you guys take a look at the book, because this is a very, 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 very nice book. Brazil's book in functional analysis. It has like the core results plus some additional discussion, but the corollaries and the propositions, the consequences that he puts are very, very interesting. It's perhaps my favorite functional analysis book. I mean, I know there are several other books in the market, but I can't help it but coming back to this one. I guess you just become fond of what you studied from. So I studied from this book when I was a grad student. So whenever people come to me and say, "Hey, why don't you check this book? It's so nice." I feel a bit rigid to move. I like the classics. But yeah, let's see. So let's see a couple of consequences of this. So let's see, corollary. Let me write down and then we prove together. So let's say you have E and F Banach spaces. Let Pn, let's say, a countable family of linear and bounded operators from E to F, a sequence such that for any x in E, Pn of x converges. As n goes to infinity to a certain limit, which we call P of x. Okay, then the claim is that A, the sup in n of the operator norms of these guys, is bounded. B, this new operator that we created here, is actually linear, and C, its bound verifies this thing. Okay, so suppose you are in a situation where you have two Banach spaces and a sequence of operators from linear and bounded operators from 1 to another. Okay? Assume that for every x in your source space E, the sequence Tn of x converges on the other side to a certain point that you baptize to be T of x. Okay? This is the conclusion then. So then these operators Tn must be uniformly bounded. This new operator that they created, T, actually is a linear and bounded operator, and its norm loses to the limit of the norms of the Tn's. Now you don't have to memorize these corollaries. I think when you work on this on these things, you should actually learn and perhaps the statements in how to use the main theorems, and some of the corollaries and consequences and propositions you will be like remembering more frequently when you start using them more frequently, right? So this is not something that you should memorize and bring with you for the rest of your life. This is just an application. This is what you should learn. Banach, Hahn, the uniform boundedness principle. So why is A true? So A is a plain and simple application of the theorem before, right? So if for every x in E, the sequence Tn of x converges, then of course it's finite. The sup of the norm is finite. Okay? So it's pointwise finite, then the supremum of the norm, the operator norms of all the guys is also finite. So A is a consequence of the previous theorem. B. Now, yeah, why is it linear? This new operator that they created, right? So this new operator that they created, well, I mean, if you have Tn of, say, x plus y, this is obviously Tn of x plus Tn of y, right, by linearity for each n. So in the limit, this will go to T of x plus y. In the limit, this will go for T of x plus T of y. So this should be equal to this. So this, you can add x and y, you can obviously multiply by a scalar. So it's linear. Why is it bounded? So this takes care of the linear part, so it's linear. Why is it bounded? Well, sorry? Because of
Sorry.
yes, because of this conclusion here, right? Yeah, exactly. So by the previous theorem, right? So by the uniform boundedness principle, let's say uniform boundedness principle, you also had that what? Ti of x, Tn of x was less than or equal than a certain c times. So this is an f, this is an e. Okay? So obviously when you pass to the limit, this T of x will keep being bounded. This implies that T is bounded. And finally, if I want actually an estimate on the operator norm of T, well, we have to actually refine this thing, right? So Tn of x of f is less than or equal than this is proof of C. It's less than actually the norm of Tn with f times. Okay? So if this is true, when you pass the limit, this n goes to infinity, T of x on this side will be less than here. You just have x. And here you have a bunch of numbers that you know it's bounded, it's uniformly bounded, but you can actually choose a sequence, a subsequence that goes to the limit infinite, right? If you want the best possible inequality here, so this will do as low as possible as the limit infinite. This inequality is true, so this means that the operator norm of T has to lose to this limit.
So, in what sense are we taking the limit here? The thing goes to infinity.
In what sense?
Yes.
Where? In which part?
Where we pass from the operator Tn of x to Tn.
In this sense? So Tn of x, T of x is the limit of Tn of x, pointwise, right?
Okay.
So I'm taking this, here I'm taking, here I'm taking just as the sequence of real numbers, right? This is just, this is a real number, the norm of f converges to the norms. So if you are in a space where your xn converges to x in a certain space, f, so the norms must converge, right? Okay?
Minus or just no?
Say that again.
Point right converges and it's not okay. No.
Yeah, because conversion in a certain, I say that a certain yn converges to y in a certain
That
space.
also continues.
Yeah. This goes to 0, right? So, yeah. This is equivalent, the same way. This implies that y goes to yn. Any sort of triangle inequality that we want there. Norm is continuous, yes. The norm is continuous in the metric generated by the norm.
I think this one is not equivalent because, for example, in the spaces, there are some theorems, is not. I mean, the last two parts, no convergence by norm.
No, I'm not, well, okay, I'm not saying that this is equivalent to this. This just implies, okay?
Yes.
This is equivalent to this. This is a definition. This implies the convergence norm, okay? Yes, absolutely. This doesn't go the other way. All right. Okay, so we have this last application. Let me show you another application which I think is actually cuter than this. And then we finish for today. Let me state here and then we prove. Okay, good. Now the corollary. Let G be a Banach space. Let B be a subset of G such that the following thing holds for any F in the dual of G, the set f of b, which is f of x with f belonging to x belonging to b, is bounded. Assume this, then b is bounded. This is one. Mistake in two parts and then you prove the other one. Let B star belong to G star be such that for any x in G, the set B star of x. Bounded to R, okay, it's supposed to be in R. Then B star is bounded. Let's just take a look at this situation to finish the class today. Look. So what I'm telling you is the following. Let G be a Banach space. And let B, so here you have your G, your Banach space. Here you have a certain crazy set B. Okay? I'm assuming that for any F in the dual space G star any linear functional, the set f of B, the set of images of this set B, this is the set of f of x with x belonging to B, is a bounded set in R. Okay? The conclusion is that this B must be bounded. The set B must be bounded. Okay? Now remember, let's try to adapt the situation to use the Banach-Steinhaus theorem. Banach-Steinhaus theorem, I had a bunch of operators, Ti, going to a certain space E to a certain other Banach space F, that they were pointwise bound. So Ti of x was pointwise bound for each x. Let's try to think about how can I do this in this situation. So here my
E is G.
My E
G and the F is R.
is going to be G. So my space is G.
F is
My F is going to be the field of scalars R. And for every x in the set B, for every x in the set B, let us consider the operator let's see if I'm doing this correctly. For every x in B, let us consider the operator
We know that there's...
yes, let's consider. Maybe this is not right. Let's see. For every x in B, let me consider the operator Tx. Let me consider the operator Tx that will act. So maybe it has to act on G star. So maybe I want to put here G star. So I will take Tx and I will evaluate this guy in a certain function f. I will define it as just being f of x. Okay, so now shuffle your head a little bit to adapt to the previous notation. Okay, x here is not what x was before. So x here is what I was before. Okay, so let's take the following set. So I'm going to take as before, my E is going to be the G star, the dual space of G. My F is going to be R. For any x in the set B that I'm considering here, I'm going to consider the operator which I call Tx, that goes from G star to R, that takes a function of f and sends it to the number f of x. Okay? This operator Tx is linear. If I take two functions f plus g, so f plus g of x is f of x plus g of x. And if I take lambda f, I just put lambda f, so it's linear. Okay, so these are linear operators. Moreover, so Px, I want to show that Px is linear. That's okay. Px is also bounded. Tx is also a bounded operator, right? So Tx of f modulus is equal to modulus of f of x. She loses to modulus of f. So this is this. This is just a number. Tx of f is equal to modulus of f, that loses to the norm of f in G star, norm of x in G. So for fixed x, if I'm fixing x, this operator here is taking a function and it's sending somebody which is less than this number times the norm of the function. Okay? So this is a bounded operator. So this operator Tx For each fixed x, they are linear and they're bounded.
But it is x. The norm is x, right? The norm is the same as the norm of x.
Yes. Okay. It's sufficient to say that the norm is at most x,
Okay.
but we can construct the functions that norms that attains this norm.
We already constructed.
Yeah. It's linear and bounded, and what you're saying is that what this implies now, for any f in the dual space that this set is bounded, this translates to Tx of f, so this set sup, when x runs over this ball, of Tx of f, this is bounded. For each f. Do you guys agree? Now if I fix a point f, and I take the supreme where x runs over the set of indices, the x of f is bounded. This is what's this saying, right? So if I fix f, the set f of x when x runs over b, this is bounded. Okay? Okay, so now I can apply the uniform boundedness principle. Remember, x here is just the set of indices. F is actually my element, my pointwise guys. So by the uniform boundedness principle, or the Banach-Steinhaus theorem, what we have is that these guys, these operators Tx, the sup of the operator norm, Tx, when x runs over this b, is bounded. Yeah, but as you said, we have seen that this norm, yes, we have constructed before the norm of this operator here, Tx. For each element little x, we know a function of f that attains its norm in that guy. We have constructed this before. So this norm here is essentially the norm of x in G. Okay. Yeah. In this spec here, I'm using the norm of Tx. Norm of this operator Tx is actually norm of x. You don't have to use this, but if you want, I mean, that's okay. I mean, you don't have to use this. If you want, the sup of Tx is less than c. This actually means that Tx of f, if you want, is less than c times norm of f, right? Right? It's uniformly bounded. This is f of x. Yes, f of x. F of x loses to a certain number times, oh well, this is okay. For any x in B and any f in the dual space. Okay? Now I can just take this as this, yeah, this, I can just, well, I need some space here. Okay, so let me just conclude. We have already proved this statement. Let me write maybe a few more lines. So this implies that f of x, which is modulus of Tx of f, loses to a uniform constant times the norm of f in G star. Okay, so for all x in B and all f in G star. This means that if I took the supremum of f of x on this side over all f in G star, so let's get norm of f in G star is less than or equal than 1, this is going to be less than or equal than c. If I just restrict myself to functionals which have norm less than or equal than 1. And we have seen that by the duality statement, if I fix x and if I take the supremum of f of x over the unit ball of the dual, that this is norm of x, which is less than or equal than c for all x in the set P. So this is to say that the set is bound. Okay?
Why we use Banach? I mean, for example, we never use G because we use G that one, and this is the dual space or always Banach space. So
Absolutely, you're right. We just needed G here to be a norm vector space because then G star would be Banach and then we could run this whole argument. That's okay, but for the item 2, you will need G Banach. So I just put the two of them together. So this has an item 2 that I wrote there. I leave to you as an exercise. You will change the roles of F and X in this proof. And your E is going to be G now, and then you need Banach in this for second case, okay? But for the first item, you don't actually need it. Okay, well today we have seen this. Sorry for the delay. Let's finish here for today, okay? See you guys on Friday.